Hey everybody, this is the supplement for week 9 on section 16.6 parametric surfaces and their surface areas. So just a quick reminder, recall that a curve in 3D, which is a 1D object embedded in a 3D space, can be defined parametrically as r of t equals x of t, y of t, z of t. So we take one variable as input and give a three-dimensional vector as the output. And this makes a one-dimensional object in a three-dimensional space. So analogously, we can think of a surface in 3D, which is a 2D object embedded in a 3D space, as a vector consisting similarly of x, y, z, but where they are functions of two variables and therefore r is a function of two variables. So r takes two variables as input, u comma v, a point in the uv space, and gives as output a three-dimensional vector in the xyz space. Okay, so let's just first look at describing some of these surfaces given parametrically. So here we have r of uv equals cos u, sine u, comma v. I know sometimes the u's and v's in the math font in Microsoft can be a little hard to tell apart, but cos u and sine u, and then v in the third component. And here we're taking u between 0 and 2 pi and letting v range over the whole real line. So one thing that we can note is if we hold v constant, then we get x and y, or cos u and sine u. That's a circle in the xy plane, or a plane parallel to the xy plane. And if I hold u constant, then I have some specific value for x and y, and I'm letting z range. That's just a vertical line, kind of parallel to the z-axis. So if I take, for instance, v equals 0, that sets z equal to 0. And then I just have x and y, or cos u and sine u, just a circle in the xy plane. So this would be like z equals 0. Or in general, for z equals z naught, which would correspond to v equals v naught here. This is v equals 0. We have some circle maybe above or below the xy plane. And then we also note for a given u, let's say u equals u naught, that picks out a point on this, say, circle in the xy plane, and then we just can vary v whatever way we would like. We can vary the height whatever way we would like to get a vertical line parallel to the z-axis. So we see our picture looks like this. We see it's a cylinder. And we see that these tracings, which are quite important, when v is constant, we end up getting circles that are parallel to the xy plane. And when u is held constant, we end up getting vertical lines parallel to the z-axis. Okay, let's look at example 2. Here we have a more complicated looking surface. X equals r cos u sine v, y equals r sine u sine v, and z equals r cos v. And here u can go between 0 and 2 pi, and v just between 0 and pi. So v is stuck between 0 and pi. And this might be a tough one to dissect if we didn't really have a pretty big hint, but we have seen cylindrical coordinates already, and this looks a heck of a lot like cylindrical coordinates. or I'm sorry, spherical coordinates. I have cylinders on my mind from the last example. We recognize this parameterization from spherical coordinates, where normally we would have a theta here and a phi here, but calling them u and v is of little consequence. We see that this is the parametric representation of a sphere. Note that u goes between 0 and 2 pi. That's our kind of parallel to the xy plane direction. So that goes all the way around. But v, the one that's kind of the deviation from vertical, that one only goes from 0 to pi, because again, we only want to trace out one side and then wrap it all the way around to flesh out our whole sphere. So we wouldn't want to make the mistake of v going between 0 and 2 pi and kind of tracing out the sphere twice if we did that. So v only goes from 0 to pi. If I hold v constant, then my height is just constant. My z value is just constant. And I end up with some number cos u and some number sine u for x and y. That's a circle parallel to the xy plane where the radius is maybe varying a little bit. It's dependent on v at a certain height. So if I hold v constant, say v equals v naught, I'm looking at a circle, say like this maybe. I'm looking at a line of latitude. I always used to get latitude and longitude confused until my wife told me the mnemonic lat flat. So latitude lines are flat. So this is a line of latitude on this sphere. And then what if I hold u constant? Then I have like some number sine v, some number sine v, some number sine v, some other number sine v for x and y, and then some number cos v for z. Well, I note that x squared plus y squared gives me r squared cos u plus r squared sine u. That's just r squared. And then times like sine squared v. So this is just going to pick out, say, some number on our x squared plus y squared equals r squared, kind of great circle at the equator here. And then we're going to be going around this direction for our kind of sine v and cos v contribution. So this u equals u naught. If I hold u fixed and let v vary, I'm going around one of these, you might call it a great circle, or one of these lines of longitude. Okay, example 3. I know another way that I can think about a surface in 3 dimensions is, say, having some domain of interest and some function z equals f of x comma y. So I plug in x comma y's in that domain and I output a height dependent on the function. And that gives me a surface as well. That's another way that we described surfaces in the past. So here's x and y. Can I describe such a surface parametrically? And yeah, it's actually quite easy to do once you kind of see the trick. Let's just let x equals u, let y equal v, and then z will be simply f of u and v. So we're basically just setting x to be u, y to be v, and then we see that u comma v is in the same domain as before. if I hold u constant, if I hold x constant and let y vary, I'm moving along a curve like that on my surface, along a curve parallel to the y-axis. And if I hold v constant, then I'm moving along a curve parallel to the x-axis on my surface. An example 4, find a parameterization r equals xyz of uv to represent the surface obtained by rotating x equals 1 over y for y bigger than or equal to 1 about the y-axis. Okay, let's get a picture of this first. All right, so x equals 1 over y. So y is, we can kind of treat it like an independent variable here. Here's y equals 1. And then x equals 1 over y is going to look kind of like that. As I rotate this about the y-axis, I end up with a figure kind of like this. This is the so-called Gabriel's horn or Great Gabriel's trumpet. Has a couple of different names. And you might have seen it in calc too. It has the interesting fact that the surface area is infinite while the volume is finite. So kind of a counterintuitive fact. Now, something that I recognize here is if I pick y to be a certain value, if I fix y, then I end up with a circle parallel to the xz plane. So that cross section parallel to the xz plane is going to be a circle by the fact that I rotated the function about the y-axis. So if I fix y naught, I have a relation between x and z. And in particular, what's the radius of this circle? Well, the radius is just the x value, or it's the value of x at y equals y naught. It's it's 1 over y naught. So for a given y equals y naught, my tracing would be a circle of radius 1 over y naught in the x, or in a plane parallel to the xz plane. So what can I do then? Well, I suppose I could just, I need to find x, y, and z in terms of u and v. Let me maybe just choose to set y equals v. And then I want x and z to represent a circle of radius 1 over v. So I need radius 1 over v times, let's say, cosine u, and 1 over v sine u. Here v goes from 1 to infinity, and u goes from 0 to 2 pi. So this would be my parameterization. 1 over v cos u for x, v for y, and 1 over v sine u for z. And a little resource I put up here. This is a nice little widget that somebody made on GeoGebra. You can type in your x, y, and z parameterizations for this surface or for some of these up here as well. And you can get a tracing of the surface, and you'll see that indeed this parameterization traces out the surface as we would expect. Okay, so moving on to the next topic then. Now that we have a basic idea of the algebraic and geometric structures of parameterized surfaces, let's take a look at the calculus of such surfaces. So we have the idea of grid curves, and then of course, tangent planes and normal vectors. So as an aside for the following, we assume that we have component functions that all have continuous first partials. That is typically an assumption throughout much of chapter 16, even though maybe here and there I maybe forget to explicitly say it. So we say that a grid curve to a 2D parameterization is a 1D curve where one of the variables is held constant. So these things that we drew up here, like these green circle and line, these lines of latitude and longitude, these kind of these curves parallel to the X or Y axes in a sense, or this circle here where we see is holding V constant and letting U vary, or maybe one of these lines where we hold U constant, the rotational direction constant, and allow V to vary. Those are called grid lines or grid curves. And this is something that we've seen before. We're just seeing it now in a slightly different context. We saw this before when we talked about partial derivatives. So we can, again, think of a surface in 3D. It has maybe some grid curves like this. And then we can consider the tangent vectors to these grid curves. We consider that there's a tangent vector to the green one, and I suppose I've run out of colors, but a tangent vector to the blue curve. And then, of course, these two vectors can trace out a tangent plane with a normal vector to this surface. Again, this is all stuff that should be familiar from our discussions on partial derivatives and so on in the past. We're just reimagining this from the standpoint of parametrized surfaces. So the underlying ideas are all the same, but it just has a slightly different surface level look to it. So if we want to consider these tangent vectors, these like red and black lines over here that are tangent to those grid lines, we could say that the derivative with respect to u of r of u comma v naught, so holding v fixed at a certain value, makes r just a function of u, and we're traversing one of these grid curves. And of course, at a certain point, we would have dr du is the partial of x with respect to u evaluated at u comma v naught, and the same for y and z. And then similarly, if we go along the other grid curve, we of course just are allowing the other variable to vary and taking the partial derivatives with respect to the other variable, in this case v. And if ru and rv are not parallel, then we say the tangent plane to the surface at the point u naught v naught going through r of u naught v naught, going through this point of interest here where we're taking the derivatives, has the normal vector ru cross rv, dr du cross dr dv. Okay, so let's look at an example. So we're going to consider this helical ramp, r of uv equals u cos v, comma u sine v, comma v, where u can vary between -1 and 1, and v between 0 and 2 pi. So this, I'm going to try to draw it here. This looks like a helix like this. But this tracing of a helix would only be, for instance, maybe when u equals 1. When u equals -1, we would get maybe a different tracing of a helix. And then as u varies between -1 and 1, as we hold v constant, we get kind of sideways connections like this. I'm not doing a super good job of drawing it, but it's a little bit like if you took a long strip of maybe of tape, or of, like, I'm thinking of, like, what is it, Laffy Taffy or something, that, or like fruit roll-ups or fruit by the foot or whatever. I don't know if they still make that or not, but if you took a long strip like that and kind of twisted it around 360 degrees end to end, that would give you kind of a twisted strip like this that would give you a helix. Kind of hard for me to draw it in 3D, but the book also, I think the book has a picture of this. Or of course you could use this GeoGebra widget to get a better picture. But it has the feeling of like a string of DNA or something, if with all those little ladder rungs, if you kind of fill it in between them as well. Okay, so let's compute the normal vector in the tangent plane at this point, 0, 1, pi over 2. So the first thing to note is that this is an x, y, z coordinate. What is this in terms of u and v? Well, I know that I'm claiming that u cos v is 0, u sine v is 1, and v is pi over 2. So equating our parameterization R with this point gives us these equations. Well, this gives us right away that v has to be pi over 2. So then these two tell me, well, cos of pi over 2 is 0. Well, that's vacuously true. And sine pi over 2 is 1. So this tells me tells me u has to be 1. So this xyz coordinate is equivalent to uv equals 1, pi over 2. Okay, so I would like to compute the normal vector in the tangent plane. So I need to find my partials, take their cross product, and go from there. So dr du is, well, that's just cos v. And then sine v. And then 0 in the third component. The third component is only v, so its u partial is 0. And dr dv is negative u sine v, u cos v, comma 1. We want to take their cross product. Didn't leave myself nearly enough room here. So taking their cross product, at the end of all of this, I get what? I times sine v times 1 minus 0. So sine v in my first component. I get j times 0 times negative u sine v. So that's 0 for the first bit of j, and then minus j times cos v times 1. So minus cos v in my second component. And then I get k times cos v times u cos v. So k times u cos squared v minus k times minus u sine squared v. Well, that's k times u times cos squared v plus sine squared v, or that should just be u in my third component. So this is my normal vector. Maybe I'll call this n tilde. It's not a unit vector necessarily, so I don't want to really call it n bar. Like that was kind of what we used for unit normal in the past. So maybe I'll give it a different name, n tilde. It's a unit vector, or sorry, it's a not necessarily unit vector that is normal to my tangent plane. And n tilde at u comma v equals 1 comma pi over 2. Well, that is sine of pi over 2. That's 1. Minus cos of pi over 2 is 0. And then u is just 1. So this is a normal vector to my tangent plane. And then my tangent plane, of course, well, it's going to be what? It's going to be my x normal times x minus x naught is 0. So I'm going back to my x, y, z coordinates now. Plus my y component of my normal times y minus 1. Plus my z component of my normal times z minus pi over 2 equals 0. Or I just get x plus z equals pi over 2 for my tangent plane. And it has this normal vector. As an exercise, you can look in the book. The book does an example of finding a parameterization of a plane. Maybe ask yourself, well, if I, instead of describing this plane in terms of x, y, and z, if I wanted to describe it in terms of u and v, how would that plane look in terms of u and v? So maybe leverage that example, try to bring that over here and see if you can describe this tangent plane in terms of u and v instead of an x, y, and z. Okay, so moving on now to surface area. And again, this is kind of a topic that we've seen before. If I have a surface, and I imagine it's broken up into some small bits of surface, I take an arbitrary little bit of surface, and I know that this little piece of surface here is approximately equal to its tangent plane. Again, for small, say dx and dy, its tangent plane looks like RV, RU. It looks like the plane spanned by these vectors, RU and RV. This is the tangent plane. And the area is approximately the cross product of RU and RV, the length of that. So definition, if we have a smooth surface S given by this parameterization, then its surface area is the double integral of length of RU cross RV dA. Okay, let's look at a couple of examples. First, let's calculate the surface area of a sphere of radius r. So a pretty classic problem to do. So here I have a sphere of radius big R. I think my bottom of my sphere should come down a little more to make it look a little better. So here's my sphere of radius R. And if we refer back up above or think of our spherical coordinates, we get x equals r cos u sine v, y equals r sine u sine v, and z equals r cos v. And here u goes between 0 and 2 pi. V between just 0 and pi. And we want to compute our u and v partials. So dr du is negative r sine u sine v, r cos u sine v, and the u partial of r cos v is just 0. And then our v partials are cos u cos v, r sine u cos v, and negative r sine v. We want to take the cross product of this. I'll leave the details as an exercise, but we should end up with the following. In the first component, negative big R squared cos u sine squared v. In the second component, positive R squared sine u sine squared v. And in the third component, we get some cancellation and we get r squared sine u cos v. Just double check that I've copied all of that right. That looks good. And then the length of RU cross RV, we get a lot of cancellation from Pythagorean identities, and we end up with just R squared sine V. So that is what we were looking to integrate over this region. So I want to integrate u equals 0 to 2 pi, integral v equals 0 just to pi of r squared sine v dv du. Note that if we made the mistake of integrating, say, v equals 0 to 2 pi, the translational symmetry of sine v, well, that's going to give us just a 0. So we'd know that that wasn't right. So we got to integrate v equals 0 to pi. And so I get r squared that comes out. The integral u equals 0 to 2 pi du. Nothing in the integrand nor in the bounds of v depends on u. So that's just a 2 pi. That integral u equals 0 to 2 pi du can all just come out in front. And then I have negative cos v from 0 to pi. This is cos v from pi to 0. Well, this is just 2. So I get 4 pi r squared, the familiar surface area of a sphere. So probably the most cumbersome part of this is the part that I skipped over here. It's not that bad. It's just kind of a lot of writing. But the math itself isn't that bad. And then when we take the length, when we square each of our components and add them together, just start factoring things out, combining together sine squareds plus cosine squareds, and you're going to get a lot of cancellation. And we end up with just this bit to integrate. As an exercise, you can try to calculate the surface area of the cone, x squared plus y squared equals z squared, lying above the disk, x squared plus y squared less than or equal to 4. And the answer is the surface area is 4 root 2 times pi. And as kind of a hint, if you want to pause the video here and try to work out the parameterization yourself, that's a good exercise. But I'll give a little bit of a hint here for the parameterization and then leave the details of calculating the area to you. So I have a cone like this, and I see that if I pick z equals z naught, then what I'm left with is a circle parallel to the xy plane. I'm left with x squared plus y squared equals some radius squared. So if I fix the z value, that gives me a circle in the xy plane, and I know how to parameterize this. So I might want to pick a parameterization like, say, let maybe z equals v, and then x will be something cos u and y will be something sine u. And then maybe think about this a slightly different way, possibly to figure out what that radius should be. Or it might be obvious to you looking at this. Okay. So we think about it geometrically, that gets us this far, and then maybe a different way of approaching it geometrically or going back to the algebraic structure will give you a hint as to what ought to go in front of here. And then at that point, you just do your kind of same strategy is up here. It'll the details will look pretty similar, but I think will be a little bit simpler. I do the same strategies up here, take the partials, their cross product, the length, and then integrate, and you should get 4 root 2 times pi. Okay, so moving to the last example. Calculate the surface area of the function z equals x plus y squared, where x is going between 0 and y between 0 and 1. So what do I have here? Well, my domain D in x and y, well, y goes between 0 and 1, x goes between x equals 0 and x equals y. So this is my domain. Or here I have x, y, and z, and y is going from 0 to 1. X also comes out to 1. So we go from 0, 0 to 1, 1, and our region is kind of along the x-axis. So these are our inputs that we're interested in. And our function is z equals x plus y squared. So it's, some function up here. I'm just going to draw some, kind of arbitrary surface. I think it will be kind of difficult to, I think, draw x plus y squared and not, it goes through the origin, not have that kind of jumble everything else up, but just to get some surface up there, we're looking for the surface area of a surface, kind of like this. Again, if you want a better picture, maybe go to that GeoGebra widget, plug in a parameterization, and you can get a better picture that way. Okay, but what's my goal here? Well, my goal is to first maybe get a parameterization, R of UV. And remember, if we want to parameterize a surface that's given by a function, we just pick, say, x equals u, y equals v, and then z is just the same function with x and y swapped for u and v. So u plus v squared. This is a parameterization of my surface. dr du is 1, 0, 1. This would, of course, in general be the variable. In general, RU would depend on U and V, but for this particular parameterization, this particular function, it doesn't happen to. And RV is 0, 1, and then 2V. So we do see that for dRdV, we get a dependence on V, no dependence on U, though. It's a fairly simple function, and picking x equals U, y equals V kind of makes those first two components pretty simple as well. RU cross RV well, my first component, my I hat component, I hat times 0 times 2V minus I hat times 1, that's a minus 1. J hat times 1 times 0, 0, minus J hat times 1 times 2V. And then K hat times 1 minus K hat times 0 is just 1. And then the length of that is the square root of -1 squared is 1 plus 4V squared plus 1, or that's the square root of 2 plus 4V squared. So that's my integrand. So I'm looking to perform a double integral. This is the area of the surface. It's the double integral of root 2 plus 4V squared. I look at this integrand and I'm a little bit suspicious. This looks like it might be a pain to integrate. So I'm going to keep in mind my multiple integral tricks. I might have to switch the integral or something like that. I might want to integrate a different way. It could turn out. Does this order work? If I integrate x going from, well, not x anymore, but x and y switch to u and v. So u goes from 0 to v, and v goes from 0 to 1. So now u going from 0 to v going from 0 to 1, du, dv. Well, this kind of nasty integrand with v's, I can integrate du just fine. And when I integrate du, I'm going to get a factor of v that's going to help out with the integration. So it looks like it's going to work out pretty well this way. If it didn't work out this way, I might have to switch the order of integration or something. That might be a trick that I could use in another context. So I have to do this as an iterated integral because my u bound depends on v. But just, I note that this is constant in u. So just integrating u equals 0 to v du gives me a v that will help out. And here I can use a substitution. If I pick, let's say, s equals 2 plus 4v squared, ds is 8v dv. I see I have a v dv. So this gives me a 1/8 integral ds. And then I have the square root of s, or s to the 1/2 power. And then I'll change my bounds. When v is 0, s is 2. When v is 1, s is 6. Or this is 1/8. I get s to the 3/2 over 3/2, or times 2/3, from 2 to 6. Or this is what? 1/12. Something to the 3/2 is like that thing times the square root of that thing. So maybe I'll write this as like 6 root 6 minus 2 root 2. That's probably about the nicest that we can make this look. Maybe I could cancel another 2. Let me go ahead and do that. So 1/6 times 3 root 6 minus root 2. Maybe that's about the best I can do. All right, so that finishes our discussion on parametric surfaces and surface areas. And next up, we just have 16.7, 16.8, and 16.9, three more sections in chapter 16, one more section this week in the lecture, and then two next week.